This is John Black, Super Chemist. We're on this playlist video series called Time and Time Dilation. This individual video is about the rotation and time dilation, repeating stuff, but acceleration in a spaceship. So you can see the difference, how they're literally the same. You got your spaceship with your photon clock and you go this way. And it doesn't have to be plates in a photon clock. It can be neuron to neuron. It jumps over the synapse. It could be two atoms in a hand on a clock. But we're going to pick this photon clock. And it's standing still. The plates are the closest distance they can be. But when you start moving, instead of this photon going up here, boom, it goes this way because you're moving. This plate is over here. So by the time you throw the photon and it gets up to this height, this is a second. This is your standing still second. It's the smallest second that you can have. But if you accelerate, you make this line longer. And look, you make it even longer here. And as you accelerate, the line gets bigger, which means the second gets stretched out or dilated. But when you go constant velocity, you keep this, whatever your line length was, that's what your time dilation is. It corresponds, your length of this line corresponds to a specific time dilation. Like this red line, it correlates to no time dilation. Then when you slow down, you're accelerating again. You make it, but you're deaccelerating. So you're making this line smaller and smaller and smaller. So therefore, your time moves faster and faster till you get stopped standing still. And you can see how this forms a right triangle. See that? So this right triangle is basically your spaceship and your sun. See how you got this distance, this dotted line? That is your horizontal. And what they like to say is that this spaceship is you, right? These vectors are all about you, because that's, everything's about you if you're a megalomaniac. But, so they say these vectors are you, and you're moving in space this way, and this way you're moving through time. If you just stood there like this, you're actually being forced to go through the time dimension at a certain rate. And then if you start going into another dimension, just like if you're going north and then you start going a little bit east, you're going out of the north dimension into the east dimension, right? And they're saying that you're going, when you start moving into space dimension, that means you're moving out of the time dimension. And so they give you this resultant vector that you want to find. Get your time dilation. Because this big line over top of this line, because this is your moving second, and this is your standing still second, so gamma is this over this. Why would you say that when you can easily say this? The vectors represent the photons vector. See, you go this way. You don't go in any other dimension. Okay, time isn't a dimension, but the photon does. That's what's funny, is if the photon does go in the, because if a photon's here, it's going to follow you, right? It's going to go on this path, but it also has to go up and down on its photon clock, or your synapses or whatever. That is two vectors. Why can't we just say it's the photons vectors, and the vectors are both, component vectors are both spatial. One's x and one's y. And this is the resultant of that, of the photons vector. And this up and down, this y, you don't get any time dilation, because you were going to do that anyway. When you're standing still, you're doing that. That contributes to getting your information carriers from one plate to the other. But over here, the horizontal, that doesn't help you get information carriers to go from one synapse to the other, or plate to plate here. See, this line is not just time, it's the rate that physics is allowed to proceed, right? The flow rate of physics. You're slowing down physics as you make this line bigger. Right? And why are you slowing down physics? Because you're wasting half of the vector of the photon going. This vector right here, all it's doing is keeping the information carriers in the same, they're just trying to keep up with you going this way, right? You're going this way. That's the only direction you're going. You're going one vector right here. This photon, though, if you're going in that vector, he is going in that vector. And he's already automatically went in this vector. So this time dilates you. The more you have to, the faster you're going this way, the more you're going this way, because none of this helps you. to get physics going. Only this helps physics go forward. Okay, so now let's look at the rotating thing. Here's the equation for time dilation for the rocket. Here is the time dilation formula for the rotating thing. They're the same exact formula. They like to put a W, for angular velocity and R for radius, and then put them in parentheses and square them. But guess what? That's the same thing as velocity squared. This is linear velocity for the rocket, and this is tangential velocity for this. But they're the same exact thing. If you're going 50 miles an hour down on a straight road, you're going 50 miles an hour. Guess what? If that road is a circle and you're still going 50 miles an hour, you're still going 50 miles an hour. 50 miles an hour is 50 miles an hour. Whether you're going straight or whether you're going in a circle, it don't matter. And you can see there's only one thing that matters in this formula. Everything else is a given, like 1, C2. These are all, you can't change them. The only thing that can be changed is this velocity squared. That's the only thing that matters when it comes to time dilation. Your velocity. The only thing that acceleration does is it makes your line grow faster. Think about it. Acceleration and velocity is the same exact thing. It's just one is velocity where it's constant, and the acceleration is velocity where you're going faster and faster. There's both velocity, but acceleration makes this line grow. Constant velocity does not make this line grow. As soon as you start going constant velocity and shut your rockets off, that's it. You're stuck with it. Whatever line length you have, that's your time dilation until you put your rockets on to slow down. It's the same thing here. Okay, so on the rotating thing, if you're standing still, just like up here, this is your photon clock. You can see it going back and forth. What happens if you drop a ball from up on this thing and you're rotating around? What would happen? It would go off pretty much at a tangent right here, just like that, wouldn't it? As you're rotating, this bottom plate will rotate up and catch it. No matter where this goes, your bottom will come up and catch it. Doesn't matter if you're going fast, slow, it will come off at a tangent. If you're going slow, then it'll move slow, but this will also move slow. They will intersect right here so that it looks like, and you will be rotating. Let's say you're standing right here. You can see that line. Look at when I rotate, the ball goes this way, but if it's 2 inches away from my head, and then now it's 2 inches from here. Now it's 2 inches from here. It looks like if you were in this situation, it would look like you are standing here and the ball is just going straight down, and hitting the bottom plate. Because that's if you drop a ball. But what if you threw the ball? Here's a train, or whatever you want to call it, a spaceship. It's got velocity going this direction. You have a photon gun here. You shoot the photon gun. It comes out at c relative to space-time, right? We all know that. But it neither loses momentum or gains momentum because of this train. It don't care. This photon does not care that this is moving. It's going to come out at c, and it's going to go in a straight line. But what if you have your gun like this, your photon gun? Yeah, it's still going to come out c relative to space-time. We all know that. But look at how it's got an angle there. Because if you shot this, you would be moved over to here by the time it hit the wall, and you would just think it went in a straight line. But my whole point here is that when you are going this way with the velocity, you don't gain any momentum by moving. You don't move any which way. You just can come out of the straight, whatever. Here, because this thing is moving, the photons move at an angle. It moves over to this way and it moves up. So it doesn't go out of straight like it should. My whole point is this. When you have a photon up at the top of the plate and you shoot it out down to the bottom of the plate, and you're just standing there, wait, that's great, whatever. But once you start rotating, you shoot your thing out, yeah, it wants to go on this tangent because of the, just that's how it works, man, the momentum. But you didn't just drop your photon, and let gravity take over so it goes like that. No, what you did was your photon was spit out. It was forced out. But just like over here, the rotating thing isn't moving this way. It's not moving up and down the way the photon is going. No, it's moving to this way. Just like this. So your thing is going to come out like over here. Look down here. See how the red line is the first line. Then you got a blue line, another blue line, another blue line. That's what, because if you go slow, you'll get the first blue line. You go faster, you get the second blue line. Faster even more, and it keeps going. It tries to get up to this thing right here where it's actually, it'll never get here, but it wants to be a tangent coming out. But your photon has been thrown out this way, so it has a momentum going this way, but it also has momentum going this way. It's the same thing. You get the red going up and down. You get the yellow line going here. That's the X. And then your resultant is this blue line, just like up here. And if you, let's say you're going slow, well, then you're going to be the first line here, and this would be what it look like. But let's say you're here. You're faster now. This would be your, see how the orange and the blue both grew, but the red stays the same. See, when you start spinning this thing up, you start spinning, 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 spinning. You're accelerating the speed and direction. And that makes the line grow. It grows from here to here to here. It's trying to grow all the way up to this size of this orange line. That is what the time dilation is. Just like up here. You're making the line grow bigger and bigger. And then what happens? When you stop trying to accelerate and you go to constant speed, your time is stuck there. Your time dilation is stuck there. This is the same way here. If you speed it up, it's going to keep going from blue line to blue line to blue line. Let's say it gets to this blue line and you make it constant velocity. Now this line is stuck there. You can't grow because you're not accelerating your speed. Yes, you're accelerating your direction, but see, that's the whole thing that's the whole point I'm trying to get to you. Yeah, when you accelerate your direction, it doesn't matter. And the way I know this is because there's no infinities from acceleration from direction on this. You can spin this and keep spinning it faster and faster and faster, but as soon as you stop and you do constant velocity, the time dilation stays where it is. It doesn't go keep. If acceleration due to direction was really making time dilate, then even though you stopped accelerating your speed, and now you're going at a constant velocity going around here, constant velocity, constant velocity. You're still accelerating your direction, and if that was time dilating you, it would keep going and keep going and keep going, and then what? You're gonna be time dilated to infinity? No, you aren't. That doesn't happen. So if that doesn't happen, that means that acceleration due to direction change, doesn't do anything to your time dilation. It's the speed, because you can't accelerate your direction without accelerating your speed at first. Then once you have your constant speed, that's it. Just like up here, you keep that same, because you're not making this line grow anymore, or this line, the blue line. You're not making that blue line grow anymore. And the blue line is connected to the orange line. You can see here it's small, this is big, this is big. Now you saw on my other videos, I had an equation that is so much easier than this crap. You could use that formula on this, but you could only do it in a retroactive way. Here, we know the hypotenuse we're given it, and we know this. Like when we have this spaceship going to the star, they tell us, oh, this is 4 light years away. Oh, this is 3 light years away. So we know the horizontal length. But here, there is no horizontal length that they can. They're not telling us anything. They're not telling the vertical. They're not telling this. They're not telling this. The only thing they are telling us is that the velocity determines the time dilation. The only thing that you need to know is this velocity squared, your tangential velocity. You get that, and you would know, you can figure out your time dilation. Or if you knew the angular velocity and the radius, that too, you can do a few different ways. You can see that this is the same exact thing as this. You got your y, which is your standing still second. You have your x, which is the distance that you're making it go into the x-axis. And then this is just your, up here, the same thing. It's the resultant of those two vectors. Just like up here, just like down here. As soon as you stop accelerating, this line stops growing. And then your time dilation is just stuck right there where it is until you slow down or speed up. Until some type of acceleration changes the length of that line.